Now, if you do this, you'll get thrown out of the amusement park. So I'm warning you right now, do not do this. But if you were to hold, say, your car keys or some heavy weight out in front of you, and at the moment that they release the clamps and that ring is allowed to fall to the ground with you on it, if you were to let go of your keys or let go of that weight, you would accelerate down at 9.8 meters per second squared. That weight would that mass would accelerate down at 9.8 meters per second squared, and it would look like it was floating weightless in front of you for the 2.5 seconds that you fell. And of course, then when the brakes go on and you decelerate, it'll keep accelerating towards the ground and they'll hit the ground before you. But as I said, if you do that, they will throw you out of the park. So don't do that. So that's a safe way to experience free fall. Another way to do it, although it's a lot more expensive, is the way that they train NASA astronauts. There is no way to turn off gravity. There are no magic rooms at NASA where there is no gravity. There's no place you can go to turn gravity off. So when we're trying to train astronauts to work in weightlessness, we have to create a way. We can't remove the force of gravity, but what we can do is create a situation where they are falling, and while they are falling, they have the sensation of weightlessness. Now, you might say, well, you could just build a big tower like this and drop them. And you could, but you only get about 2.5 seconds there. A better way to do it is to use an airplane. In the case of NASA, they used to train astronauts on an airplane called the Vomit Comet. The Vomit Comet was an old Boeing 707. It was the military version of a Boeing 707. And what they would do is they would fly the airplane up, and then as they got close to the top altitude, they would arc the airplane over, and they would let the airplane fall to the ground. They would let the airplane accelerate downward at 9.8 meters per second squared. Now, because everyone inside the airplane is accelerating to the ground at 9.8 meters per second squared, if you accelerate the airplane down at that rate, everybody inside is weightless. And when you do this, you can be weightless for about 25 or 30 seconds at a time. The reason, of course, it can't go much longer than that is the airplane is accelerating rapidly to the ground. It is not only gaining speed, but it's getting closer to the ground. The pilot has to pull the airplane out of the dive. When the pilot pulls the airplane out of the dive, you experience actually almost 2 Gs as the airplane pulls out of the dive and then goes up and does it over and over and over again. Now, the thing is, what happens to people in this airplane and what happens to astronauts when they become weightless, not all astronauts, but some astronauts, is that if you think about how you know how you're oriented in this room, right? As I'm sitting here, I know that that's up and that's down. And I know that for 2 reasons. My eyes are giving me visual clues. I can see what I know to be the floor and the ceiling up above me. But there's also a fluid in my ears. It's called my vestibular system. And that fluid is telling me, because it's being pulled down by gravity, it's also telling me that that is up and this is down. And when my eyes agree with my vestibular system, everything is okay. But if I jostle my head, if I do anything to upset that fluid in my ears, I can give myself motion sickness. Motion sickness is what happens when your eyes and your vestibular system don't agree with one another, and your body starts getting motion sickness. In the case of astronauts floating in weightlessness, well, that fluid in their ears is no longer being pulled down to the bottom. It's now free floating inside their ears, and that gives them a tremendous amount of motion sickness. And to protect itself, when you get motion sickness, one of the first things that you do is you vomit up anything that's in your stomach. And so this airplane at NASA was affectionately known as the Vomit Comet. And that's because so many people that would go on board would throw up within these first few cycles of going up and down. Eventually, you'd clear all the contents out of your stomach. You would start getting used to this fact that your vestibular system and your eyes don't agree with one another. We'll talk later on in the semester about adapting to weightlessness. It's called space adaptation sickness. Some astronauts get a mild case. Some astronauts don't seem to get it at all. Some astronauts get a severe case. And we can't always predict ahead of time who's going to get sick in weightlessness. To give you an idea of what this is like, if you would like to do this, there are companies like the Zero Gravity Corporation that today offer commercial flights that do exactly this. So they have an airplane that they have converted to doing it. And so it's quite expensive. I think it's over, I think if last time I'd seen it was over $10,000. Let's just pick Fort Lauderdale there. well, in any case, they're very expensive to do. So you can go to the Zero G Corporation, and like I said, they have an airplane where they will do this. And then a couple people have made videos like this to show you what being in zero gravity is like. This is one that the band OK Go did, where they filmed a music video inside of an airplane.
Inside down and upside up, you can feel it, feel it. Don't stop, can't stop, it's like a freight train. Don't stop, can't stop till you feel it going down. I wish I had said the things you thought that I had said. Gravity's just a habit that you're pretty sure you can't break. Upside down and inside out, you can feel it. Can't stop until you feel it going down. Upside down and inside out, you can feel it. Don't stop, can't stop until you feel it going down.
So what's really cool about that video is you'll notice that they did that in multiple takes. That is, that wasn't all in one parabolic arc, because a parabolic arc, you can only be weightless for about 25 or 30 seconds. And if you watch very carefully, particularly when they have the balls floating around and things like that, you can actually see when the airplane pulls out of the dive, everything comes down to the floor. And then what they had the actors, the singers, stand very still for those few moments when they recover from the dive, level off, climb again, and then as soon as the airplane goes through its next parabolic arc, they would pick up where they left off before. But if you watch the things that are floating around the cabin, you can tell when they're weightless and when they're not weightless. Really quite an amazing video for them to have put together. I put on there, if you're interested, you can find out, just look for Upside Down and Inside Out, and you can see a video on how they made it. Here's another example, just because it's kind of fun, of doing a Formula One pit stop inside of weightlessness.
This year the pit stops have been... This year the pit stops have been right on the mark. team never stops pushing the boundaries. We have a new directive from headquarters. Our mission is to do a pit stop in 20 seconds. In zero gravity.
Touchdown confirmed. We are safe now.
So at the end of that video, you can see right at the very end, as they pull out of the dive, how everybody comes, I don't want to say crashing down, but how everybody comes down to the floor as they pull out of the dive. So why is it then that astronauts are weightless? If you can experience weightlessness by falling, how is it that astronauts are weightless continuously? Well, let's talk about what it's like to be in orbit. And to do that, I'm going to bring up this little applet right here. And so what we've got is the Earth, and we've got a mountain on top of the Earth, and then on top of that mountain, there's a cannon. This is actually called Newton's Mountain or Newton's Cannonball. It's a famous demonstration of what goes on. And so what I'm going to do here is I'm going to fire. That little green dot represents the cannonball, and I'm going to push this button down here. I'm going to fire it. So let's think about what happens. I fire the cannonball sideways. So what happens? As the cannonball falls to the Earth, it's accelerating downwards at 9.8 meters per second squared. Imagine that that cannonball was hollow and that there was something inside the cannonball. As the cannonball accelerated downwards at 9.8 meters per second squared, whatever is inside the cannonball accelerates downwards at 9.8 meters per second squared. And it too will be weightless. As the cannonball falls to the ground, it will fall to the ground. So when we fire that cannonball to begin with, we give it some initial speed, and then it's just, or velocity, you can say it goes with that initial speed. But once it leaves the cannon, it's no longer being accelerated by the cannon. In fact, if we ignore air resistance for a second, it'll travel at a constant speed. And as it falls, as it accelerates downward at 9.8 meters per second squared, whatever's inside it will be weightless. So let's do this. Let's fire this cannonball. Okay, so I fired the cannonball, and you can see that it went some distance and it fell to the Earth. And remember, from the moment it leaves the nozzle of the cannon till it hits the ground, the cannonball is weightless. It's falling to the Earth. Whatever's inside the cannonball is weightless because it's falling to the Earth. Now let's give it a little bit more initial speed. So that initial speed was 3,500 meters per second. So let's give it initial speed. Let's go up to, let's say, 4,500 meters per second. Or 4,800 meters per second. So what's going to happen now? Well, you can imagine if I fire it faster, it's going to go further before it hits the ground. Now let's go a little bit faster than that. Let me fire it again. It goes still further before it hits the ground. And if I go a bit faster still, it's going to go even further before it hits the ground. But now, imagine that I fire it at this speed. Now as it falls to the Earth curves away from underneath it and it falls around the Earth. and it hits the person at the cannon at the very end. So for the humorous sound effect at the very end right there. When I fire this cannon, what happens is as the cannonball goes sideways, it's falling to the earth. As it falls to the earth, it's accelerating downward at 9.8 meters per second squared. Whatever is inside the cannonball is accelerating to the earth at 9.8 meters per second squared, and it is weightless. But as the cannonball falls towards the earth curves out from underneath it. And so the cannonball literally falls around the earth. And as the cannonball falls around the earth, it's in continuous free fall. So whoever is inside the cannonball is weightless the whole time. That is what we do with astronauts. Because they're moving in orbit around the earth, as they fall towards the earth curves out from underneath them, and they are weightless the whole time. So that is the idea behind Newton's cannonball. The idea that astronauts are weightless because they're in constant free fall. It's not that there's no gravity acting on them. Remember, they're being accelerated downward due to gravity. And that acceleration, actually, I should say, up at the orbit for the space station it's only 88% the acceleration down here. But they are being accelerated towards the Earth. And they're experiencing the force of gravity. It's just that they're weightless because they're falling. And here's another picture of that. So that raises an interesting question then. How does the space shuttle launch or a rocket launch? When a rocket launches, this is an actual photograph you'll see here of the space shuttle launching. Which path does it follow? So go out and do this lecture exercise. Does it go straight up? Does it go up and a little bit to the side like in B? Does it go up and then sideways as you see in C? Or does it go up and back down again in D? So what do you think of these as the correct one? What path best represents the space shuttle after launch? Go out to your lecture exercise and answer this. So what did you think on this one? Which one is the best represents the path of the space shuttle? Well, here's the thing. If we launch the space shuttle or a rocket straight up, right? The thing that you learned when you were a kid is exactly right. If you throw something straight up, it's going to come straight back down. So as you throw something straight up into the air, it's going to eventually stop and it will come back down. It will not get into orbit around the Earth. In order to get into orbit around the Earth, as we just saw a second ago, you have to be traveling sideways. And you have to be traveling sideways depending on which altitude you want to be at. But a good typical orbital velocity is about 7,500 kilometers per second. As we saw, the International Space Station is 7,660 meters per second. Sorry, 7,500 meters per second, not kilometers per second, but meters per second, or 7,660 meters per second for the space station. At that speed, you will fall around the Earth. So, for the space shuttle or a rocket to get into orbit, we don't fire it up. We have to get it going sideways. And in fact, a thing that people find surprising is that rockets spend most of their time and almost all of their fuel accelerating sideways and not accelerating upwards. So here is that photograph of the space shuttle in the end. That is what the space shuttle does. If you ever get the chance to see a launch, what you will see from the ground is that the rocket will launch upwards. But almost immediately from the moment that it leaves the launch pad, it starts tipping over on its side. Now, a rocket does have to get up above the Earth's atmosphere, so it does have some climbing that it needs to do. But it will spend the vast majority of its time accelerating sideways and not accelerating up. And if you get the chance to see a launch like this, this is exactly what you will see. You will see the rocket doesn't go straight up and just disappear high into the sky. It starts almost right. In fact, you can hear this on many launches. You will hear them say right after launch, they'll say roll program. Roll program is a piece of software that takes the rocket and starts rolling it over. Or in the case of the space shuttle, used to roll it over on its back. You'll hear it with the old Apollo launches as well. That means that as soon as they leave the tower, they start that roll program, because to get into orbit, you have to be traveling 17,100 miles an hour sideways. So you've got to spend almost all your fuel accelerating sideways. So you'll see it climb and then arc up. And then as it starts following the curvature of the Earth, you'll actually see it arc down. And if you ever get to see a launch, you typically lose sight of it, not high up in the air, but when it goes beyond your horizon. Once it gets high up and then it arcs down and goes beyond your horizon down there. All right. So gravity is the force, just to sum up where we are right now, gravity is the force that holds satellites in orbit. There's lots of gravity in space. Satellites are continuously being accelerated because their velocity is constantly changing. you'll remember that Newton's first law says an object remains in motion in a straight line at a constant speed unless acted on by a force. Now, the speed of the space station may not be changing, but its velocity clearly is, because the space station is not orbiting in a straight line. It is clearly orbiting in a circle around the Earth, which means it's being accelerated, which means there is a force acting on it. And interestingly, that force is acting on it continuously, but because its motion is in one direction and that force is at a right angle to the motion, it neither speeds up nor slows down. If it's in a perfectly circular orbit, the space station's speed would stay the same through its whole orbit. So the direction is changing, which means the velocity is changing, which means there's an acceleration. So how fast do you have to be moving to stay into orbit? We said already that you have to be going 17,100 miles an hour, or about 7,660 meters per second for the space station. How do you determine that? Well, here's the formula that determines that. It's called the circular orbit velocity. So the circular velocity required to stay in orbit, or the circular orbital velocity equation, tells you that the speed you need to stay in orbit is the square root of g times the mass of the Earth, or the mass of the body that you're orbiting, divided by your distance from the center of the body. Now, it's important to remember, this d is not your distance above the surface. It's your distance from the center of the body. So typically, on Earth, we measure orbital altitudes above the surface of the Earth, then you have to add on the radius of the Earth as well. So, for example, a low Earth orbiting satellite is 6,800 kilometers from the center of the Earth. If we plug the numbers in, g, 6.674 times 10 to the minus 11th, the mass of the Earth, 5.972 times 10 to the 24th kilograms, divided by 6.8 times 10 to the 6th meters, plug those in, take the square root, you will find out that the circular orbit velocity is going to be 7,656 meters per second, or 7.656 kilometers per second. That's 17,150 miles an hour. So this is the speed that you have to be going to orbit the Earth. All right, so the misconception is that rockets launch straight up. They don't. They actually spend most of their time accelerating sideways. All right, here are a couple more launch pictures that I like to put in. This is typically if you go down to Cape Canaveral or Cape Kennedy to see a launch, they launch out over the ocean. You're usually on land, so they usually launch away from you. And so this is what you'll typically see in a launch away from you. You'll see the rocket climb up, and then it starts arcing over, and then it arcs over, and it starts heading downward. And you'll typically, in this case, they lost sight of it because of the clouds, but you'll typically lose sight of it when it gets very, very low down there. And it's not that it's coming back to Earth. It's now that it's following the curvature of the Earth around. At Cape Kennedy, at Cape Canaveral, there's actually a pier. It's where the cruise ships come in, Canaveral Pier, and you can actually, during launches, it's a very, very popular site to go watch launches from. It can be very, very crowded on a launch day, but it's really nice because it provides a fantastic view of all the launch pads on the Space Coast there at Cape Canaveral in the Kennedy Space Center, and you can actually watch the launches go out over the ocean. So here's another question for you in the lecture exercise. Go out to the lecture exercise and answer this. Does the space shuttle have to achieve escape velocity to make it to orbit? So does the space shuttle achieve escape velocity to make it to orbit? True or false? Just go out to the lecture exercise and answer that. All right, so the first question to answer this one is, what do we mean by escape velocity? So let me go back a couple slides here and bring my little applet up again that has Newton's mountain. Remember, if I go about 70, what would we say here, about 7,500 meters per second or so, and I shoot my cannon, that the cannonball goes into orbit around the Earth. Well, what if I give it more speed? What if I go, let's say 9,000 meters per second and fire it? It follows a bigger orbit. If I go fast enough, I actually give it enough speed that it will escape from the Earth and never come back. And so that's what we mean by escape velocity. Escape velocity is the speed that you have to be traveling to escape from the Earth and never come back. Now, the escape velocity is given by this equation. The escape velocity is the square root of 2 times g, that gravitational constant, times the mass of the body that you're orbiting, mass of the Earth in this case, divided by the distance from the center of the body. You'll notice that looks an awful lot like the circular orbit velocity, right? The two of them are almost identical to one another, except now there's an extra 2 inside the square root. So that means that when you've achieved orbital velocity, you need a square root of 2 greater than that to achieve escape velocity. Or you can just use this equation to calculate the escape velocity. So let's do this for the Earth. Let's actually do an escape velocity calculation for the Earth because, again, like the orbital velocity and the force of gravity, I would expect that I could give you a problem on a quiz or a homework assignment, and you should be able to calculate the escape velocity for any planet in the solar system. So what do we have here? The escape velocity from Earth is, let's imagine that let's imagine that we're trying to escape down here on the surface. We're not starting at some high altitude. We're just right here on the surface. I want to fire a rocket and I want to escape from the Earth, ignoring air resistance. The question is, how fast does my rocket need to be going to escape from the Earth and never come back? All right. And you can imagine, by the way, I forgot to give you my little example here. I've got the styrofoam ball here. You can imagine that if I take this styrofoam ball and I throw it up, it comes back down. If I throw it harder, it goes higher before it comes back down. If I throw it really hard, it goes even higher before it comes back down. You can imagine that there is some speed that I throw this so fast that it'll actually escape from the gravity of the Earth and never come back. And that's the escape velocity. All right, so what is that for the Earth? The square root of 2gm over d. Since we're starting at the surface of the Earth, d is going to be the radius of the Earth, m is the mass of the Earth, g is our constant, and 2 is a constant. So it is the square root of 2 times g, which is 6.674 times 10 to the minus 11, times the mass of the Earth, 5.972 times 10 to the 24th kilograms, divided by the radius of the Earth, which is 6.378 times 10 to the 6th meters. Don't forget to take the square root. Probably the biggest mistake that students forget here is they do this big long calculation and then they forget to take the square root. So the escape velocity from Earth is then, if you plug these numbers into the calculator, take the square root, you get 11,180 meters per second. That's 11.18 kilometers per second, or 11.2 kilometers per second is good enough in there. So that is the escape velocity from Earth. So the misconception is that rockets need to achieve escape velocity to orbit the Earth. They do not. And in fact, we don't want the rocket to achieve escape velocity because we typically want the astronauts on board to come home, right? When we send them up to the space station or we sent them up on the space shuttle, we want the astronauts to come home. Escape velocity is how fast you have to be traveling to never come back, okay? So, in addition, the space shuttle and the SpaceX Dragon capsule, both of those, neither of them have enough energy to actually achieve escape velocity. So the space shuttle used all of its fuel to get up to orbital, circular orbit velocity. It does not have enough fuel left over to achieve escape velocity because remember, that's another square root of 2 higher, which is about 1.4 times faster than the orbital speed. And that would require a lot of extra fuel to do that. The same thing is true with the Dragon capsule, at least on the Falcon 9 that it launches on now. You could imagine launching it on a bigger rocket like the Falcon Heavy. Then you could give it enough speed to escape from the gravity, to reach escape velocity. But the Dragon capsule, the Crew Dragon on the Falcon 9 does not have enough energy to reach escape velocity. So, okay. So that is escape velocity. With the Newton's cannon, as I said, if you fire it fast enough, it'll escape and never come back. So now answer this for the lecture exercise. The Mars rovers, do they have to achieve escape velocity to make it to Mars? So answer this question. Go out to the lecture exercise. When we send rovers and spacecraft to Mars, do they need to achieve escape velocity? So what do you think on that one? The answer to this one, of course, is true. To get to Mars, not only do they have to escape from the Earth, but we have to give them even extra speed because as they go from the Earth to Mars, they're working against the gravity of the sun. And on top of that, we give them extra speed because we want them to get there fairly quickly. We don't want them to get there very slowly. And so we not only have to achieve escape velocity from the Earth, but we also have to add extra speed to fight against the gravity of the sun to get all the way out to the orbit of Mars. And then we have to throw some extra speed on top of that so that they can get to Mars a little bit faster than they would otherwise. And that makes the trip a little bit faster. So the answer to this one is true. The rovers to Mars, spacecraft to Mars, astronauts going to Mars, they have to achieve escape velocity from the Earth. All right, here's your chance to put it to practice. What is the escape velocity from the surface of Mars? So the Mars 2020 rover Perseverance is going to cache samples on the surface of Mars, and those samples will eventually be brought back to Earth. There will be some mission here in the next decade or so, and the goal for that mission will be to gather up those samples on the surface and bring them back to Earth. Of course, if it takes a large rocket to launch off the surface of the Earth and achieve escape velocity to get to Mars, they'll have to do exactly the same thing on Mars. They'll need a large rocket that can not only get up to Martian orbit, but can actually escape from Mars and come back to Earth. So the question is, what is the escape velocity from the surface of Mars in meters per second? So go ahead and calculate that. The things you might remember that you need to know is that Mars is 0.1074 times the mass of Earth, and its diameter is 0.5325 times the diameter of Earth. I'm going to let you pause it here and go ahead and work out the escape velocity from the surface of Mars. All right, how do you do this problem? Well, the way you do this problem is, first thing we need is the mass of Mars and the radius of Mars. So the mass of Mars is 0.1074 times the mass of Earth, which is 5.972 times 10 to the 24 kilograms. So the mass of Mars is, we did this earlier, but I'm doing it again anyhow, 6.414 times 10 to the 23 kilograms. The radius of Mars is 0.5325 times the radius of Earth, which is 6,378 kilometers. So the radius of Mars is 3,396 kilometers, or 3.396 times 10 to the 6th meters. Now let's just plug it all into our escape velocity equation. The square root of 2gm over r, or 2gm over the radius of Mars, so it's 2 times g times the mass of Mars over the radius of Mars, because of course the samples are on the surface. We need to escape from the surface of Mars. And so 2 times 6.674 times 10 to the minus 11th times the mass of Mars, 6.414 times 10 to the 23 kilograms, divided by the radius of Mars, which is 3.396 times 10 to the 6 meters. The escape velocity is 5,021 meters per second, or 5.021 kilometers per second. How does that compare to the escape velocity from Earth? Well, we can just do that ratio real quick. The escape velocity from Earth is 11.2 kilometers per second. From Mars, it's 5.02 kilometers per second. So it's about 45% the escape velocity from Earth. So here's the thing. To get samples off the surface of Mars and to get them back to Earth, you might wonder, why have we never done that before? Why is it that we've obviously sent astronauts to the moon and brought samples back from the moon? Russia has brought samples back from the moon without sending astronauts. They used robots to gather up samples. The former Soviet Union, I should say, has gathered samples on the moon with robots, brought them back. China just recently brought back lunar samples. Why have we never done it from Mars? And the answer is because the escape velocity from Mars is fairly significant. Remember, the gravity on the moon is significantly weaker than the gravity on Earth. But the gravity on Mars, although smaller than gravity on Earth, is not significantly smaller. To get off the surface of Mars, you're going to require a rocket that has 45% of the ability of a rocket on Earth. That is, to get those samples off the surface of Mars and achieve escape velocity from Mars is going to require a fairly large rocket. Now, we know how to get small spacecraft and rovers to Mars, but to do a return sample, you're not only going to need to get your spacecraft to Mars, but you're also going to need to get a rocket to Mars. And of course, to get that rocket to Mars is going to require an even much larger rocket leaving from Earth, carrying the rocket that gets to Mars, that's going to rocket off Mars and bring the sample back home. Because we don't have the ability to do that right now, we've never been able to bring a sample back from Mars. So when our rovers go to Mars, they contain scientific instruments to analyze the composition of the rocks, but we've never been able to bring a Martian rock home. Now, we do have some Mars rocks on Earth, and we'll see about this later in the semester, and that's because giant asteroids have slammed into Mars in the past, blown pieces of the surface out into the solar system, and then they've entered the Earth's atmosphere as meteors. And so we have found little chunks of meteorites on Earth that have the same composition as the Mars. There's little bubbles in there that have the same composition as the atmosphere on Mars. So we believe that those meteorites came from Mars. So that is circular orbit velocity. That is escape velocity. I want to spend a couple minutes talking about where both of these come from. How do we get these equations? Because it helps us think about orbits, and it helps us think about things orbiting, and it helps us, sort of cement the physics a little bit. So let's talk about what's happening. Remember that example that I used last time with the ball in the last lecture with that ball? I'm swinging the ball over my head, and what's the ball doing? Well, the ball's not moving in a straight line. It's moving in a circle because there's a force constantly acting on it, and that force is called the centripetal force, and it's caused by the tension in the string, right? As I whip that ball over my head, that string is very tense, and it's the tension of that string that's providing the centripetal force that holds the ball in orbit around me. And I know the ball is being accelerated because its velocity is constantly changing because its direction is changing. And if that string, you'll remember, if that string suddenly breaks, the ball then follows Newton's first law, which is straight line at a constant velocity, straight line at a constant speed, because it's no longer being acted on by a force because that string broke. The centripetal force goes away. Now, the question is, how strong is that centripetal acceleration or that centripetal force? Well, the centripetal force, so for an object in circular motion, there has to be a force pulling towards the center of the motion. In the case of the ball on the string, the centripetal force is ma. The centripetal acceleration is v squared over r, and so the force is mv squared over r. So it takes a bit of geometry to calculate the acceleration here of v squared over r, and we're not really worried about that in this lecture, so I'm not going to go through the argument for doing this. Just know that as that thing is being accelerated towards the center, the acceleration it's undergoing is v squared over r, so the force is mv squared over r. Well, in the case of an orbiting body, this centripetal acceleration, v squared over r, or the centripetal force, mv squared over r, has to be provided by gravity, right? In the case of my Newton's cannonball, as that cannonball orbits the Earth, it is gravity pulling it towards the center. Gravity is providing that centripetal force, and so that centripetal force has to be equal to the force of gravity. So let's set these equal to one another and see what we get. The centripetal force has to be equal to the force of gravity. So mv squared over r, where little m is the mass of my satellite, right, is equal to g times the mass of the Earth times the mass of the satellite over the distance. There's the distance between my satellite and the center, so that is r. So mv squared over r has to be equal to mass of the Earth times the mass of the satellite over r squared. So multiplying, you'll notice that the mass of the satellite here and the mass of the satellite here, they cancel one another out. And so we don't have to worry about them because they cancel one another out. So they cancel out. We multiply both sides by r. We get that v squared is gm over r. So v is the square root of gm over r. That's where we get the circular orbit velocity equation from. The velocity of an object that's in a circular orbit around the Earth, that's in a perfectly circular orbit, is the square root of gm over r. And it just comes from setting the centripetal force equal to the force of gravity. mv squared over r is gmm over r squared. And again, the little m's cancel out. We've got a little m here and a little m here. They're going to cancel one another out. The best way to put it is we divide both sides by little m, so it cancels out. And then we multiply both sides by an r, so these r's cancel out. This r squared becomes just a 1 over r. So v squared is gm over r. V is the square root of gm over r. That's how we derive the circular orbit velocity equation. So how do we get the escape velocity equation? So now that we've seen how we get that, can we use the same kind of argument to get the escape velocity equation? Turns out that's actually a little bit harder to do, because in the case of the escape velocity, as you pull further and further away from the Earth, the force of the Earth pulling on you gets less and less, right? In this case, because you're at a constant altitude here, you're at a constant distance from the center, the force due to gravity is not changing. But as you escape from the Earth, the force of gravity is constantly changing. It's constantly getting smaller and smaller. Now, you can do a calculation to say, okay, well, if I'm at some distance, what's the force of gravity? What's the acceleration at that moment in time? And then recalculate it for the next second and recalculate it for the second after that. And you might get the impression, for those of you that have had calculus, that if I talk about doing something and then a short time later calculating it again and doing it again and doing it again, that's what calculus is all about. So it would actually take some calculus to derive the escape velocity equation. But instead, in physics, sometimes when we have complicated mathematics to calculate something, there's an easier route to calculating it. In the case of escape velocity, that easier route actually comes from energy arguments. So let's talk about energy for a second. And what do I mean by energy? Energy is the ability to do work. So the unit of energy in the metric system that we're using, the International System of Units, is called the joule. Now, a joule is a small amount of energy. In fact, if I take just a cubic centimeter of water, 1 milliliter of water, it takes 4 joules of energy, 4.2 joules of energy, to raise that 1 gram of water 1 degree Kelvin. So if I just want to raise it by 1 degree, it takes 4 joules of energy. So it gives you an indication that a joule is a small amount of a unit of energy. To give you an idea of how small a unit it is, if I were to be in a classroom and to walk at 2.2 miles an hour, which is 1 meter per second, as I'm walking with that, my kinetic energy, my energy of motion, is about 58 joules. And another way to think about a joule is a barrel of oil. A barrel of oil contains about 10 billion joules of energy. So that's energy. And the unit we use is the joule. Now, when we talk about how quickly we're using up energy, we term that power. Power is the rate at which energy is used. And in the metric system, the rate of usage of energy is called power, and the unit of power is the watt. And a watt is 1 joule of energy per second. So I'm sure you're all familiar with a watt, right? You've got a 100-watt light bulb. What we mean by a 100-watt light bulb is it uses 100 joules of energy every second to power the bulb. To give you an idea of how bright, luminous our sun is giving off 3.8 times 10 to the 26th joules per second. That means that its luminosity, how its intrinsic brightness, how much energy it's giving off every second, is 3.8 times 10 to the 26th watts. That's how bright our sun is. Compare that to a 100-watt light bulb. By the way, 3.8 times 10 to the 26th, that's a 3 and an 8 followed by 25 zeros. So if you want to write that out, you can see how big that energy is. There are many different forms of energy, and one is kinetic energy. And kinetic energy is just the energy of motion. And so if we have an object with a mass m, and it's moving at some velocity, v, the kinetic energy is 1/2 mv squared. So the energy, the kinetic energy, is just simply 1/2 times the mass times the speed squared, the velocity squared. So let's do that calculation for me walking across the front of the room. So here's a lecture exercise for you. What is the kinetic energy of Mr. Murphy when he walks across the classroom with a speed of 1 meter per second? Okay. Assume that I have a mass of 115 kilograms. So I'm walking, I have a mass of 115 kilograms, and I'm walking at 1 meter per second. How much energy did it take to get me up to that 1 meter per second? So go ahead and go out to the lecture exercise, pause the lecture here, and answer this question. How much energy does it take to get Mr. Murphy moving at 1 meter per second? All right, what did you get? Well, the kinetic energy is 1/2 mv squared. So it's 1/2 times my mass, which is 115 kilograms, times my speed, which is 1.0 meters per second squared. When we use this equation to get the answer in joules, mass always has to be in kilograms and the velocity always has to be in meters per second. And when we plug those numbers into the calculator, we'll see that it takes 58 joules of energy to get me moving. Now, kinetic energy is just one form of energy. We've also got something called potential energy. Potential energy is stored energy, and that's energy that has the potential to do some work. So I want you to list for me some forms of potential energy. So go out to the lecture exercise, think back to high school chemistry class or earlier. What are some forms of potential energy? Again, potential energy is stored energy. It's the ability to do work. All right, what did you get for some forms of potential energy? Well, the forms, I'm just going to list a couple here. There are many more than this. There are chemical potential energy. A really good example of this is rocket fuel and oxidizer. In that first stage of the Saturn V rocket there, they had a huge tank of rocket propellant 1, which was the kerosene, and then they had liquid oxygen. When we bring rocket propellant 1 and liquid oxygen together, there is the potential to release energy. That's stored energy. And the only way to release that is by oxidizing the fuel, literally burning the fuel. And in burning the fuel, we release that stored chemical potential energy and we turn it into thermal energy, which is also just kinetic energy, the energy of motion or heat energy. There's mechanical potential energy. Think about a rubber band, taking a rubber band and stretching a rubber band. When I stretch a rubber band and hold it stretched out, it has the potential. There's energy stored in that. Think about a spring. When I compress a spring, I've stored energy in it and it wants to spring back. There's gravitational potential energy. I have a ball here. When I sit it on the desk, it has it has no potential there, but when I lift it up, I put energy into lifting it up, and that stores energy so that when I let it go and it falls, it releases that energy. That's gravitational potential energy. There's electric potential energy. There are many other forms of potential energy, but and you can list some of them in the lecture exercise, but these are just some of the ones that I put down here. So let's talk about gravitational potential energy. When I take an object like this, the gravitational potential energy of that object is G times the mass of the Earth, if we're talking about the potential energy with respect to the Earth, times the mass of the ball divided by the distance between the center of the ball and the center of the Earth. Don't worry about where this equation comes from. An important thing to notice with it, though, is that the gravitational potential energy there is negative, but don't worry about that. So that's the potential energy. Now, I'll explain why I'm talking about this here in a second. So let's imagine that we've got a rocket and we want to fire it at the escape velocity so that the rocket escapes from the Earth and it never comes back. The total energy of a system, the total energy of a closed system is a constant. That means the energy is conserved. So the energy you have at the beginning has to be the energy at the end. So imagine me taking this ball and I want this ball to escape from the Earth, okay? So I'm going to throw it at some really fast speed. Well, when I throw it at that really fast speed, it has some kinetic energy. And it has, because it's down here on the surface of the Earth, it has the potential energy down here is at a maximum. Is at a minimum. As I throw it upwards, it's going to go slower and slower and slower. Because what's happening is it's turning that kinetic energy, as it gets slower, its kinetic energy is getting less and less, and it's turning that into gravitational potential energy. That is building up more and more potential energy until eventually, if I throw it at exactly the escape velocity, when it gets infinitely far away from me, it'll stop moving. That is, if I throw something with the escape velocity off the surface of the Earth, it'll always keep moving away from the Earth, but it'll always be getting slower and slower, and eventually it'll come to rest infinitely far away from me. So let's think about this for a second. The kinetic energy, the energy of motion, and the gravitational potential energy to begin with at the start have to be equal to the kinetic energy and the potential energy at the end. So as the ball pulls away from me, as the rocket pulls away from the Earth, it gets slower and slower and slower. And if it has exactly the escape velocity, it comes to rest at infinity. Go out to the lecture exercise and answer, what is the kinetic energy of the rocket at infinity. And the hint here is, remember, at infinity, its velocity is 0. So the kinetic energy is 1/2 mv squared. So go ahead and answer this question. What is the kinetic energy of the rocket at infinity? So what did you come up with for this one? Well, it's fairly easy. The kinetic energy is 1/2 mv squared. V is 0. So the kinetic energy is 0, right? It starts with a lot of kinetic energy, and then it gets slower and slower as it gets further away. And when it's infinitely far away, the velocity is 0. So it has no kinetic energy at the end. So in this equation where we said the kinetic energy at the beginning and the gravitational potential energy at the beginning have to be equal to the kinetic energy at the end and the gravitational energy at the end, this one, the kinetic energy at the finish is going to be 0 because it's not moving. Well, what's the potential energy at the end? The gravitational potential energy is minus g, the mass of the Earth, the mass of the body divided by the distance. What is the potential energy of the rocket at infinity, right? I throw this ball, and when it gets infinitely far away from me, when it finally stops moving infinitely far away, what is the gravitational potential energy? And think back to high school math. If d is very, very big, so that d is infinite, what happens when you divide by an infinite number? What does the potential energy become? So go ahead and answer that question out in the lecture exercise right now. This one is a bit trickier because it requires remembering in math what happens when you divide by a really big number. So just remember, as I divide by a big number down here, this is small. If I divide by a bigger number, this is even smaller. If I divide by a really big number, this gets really, really tiny. And if I divide by infinity, this becomes 0. So the gravitational potential energy out at a distance of infinity, because the gravitational potential energy goes as 1 over the distance, and the distance is infinity, that means the gravitational potential energy is 0 out there at infinity. Okay? So here's the thing. At infinity, the kinetic energy is 0, and at infinity, the gravitational potential energy is 0, so everything on this side of the equation is equal to 0. So now let's do a little bit of algebra. The kinetic energy at the beginning and the gravitational potential energy at the beginning are equal to 0. So that means the kinetic energy at the beginning is equal to the negative of the gravitational potential energy at the beginning, right? I just subtracted Eg from both sides. Well, the kinetic energy is 1/2 mv squared, where v is the escape velocity, because I said I threw this at the escape velocity to begin with. And that's just the negative of g times the mass of the Earth, the mass of the ball over the radius of the Earth squared. Well, now let's do a little bit of algebra. Multiply both sides by 2. The 1/2 and the 2 cancel out, so I get 2gm over re. I have the mass of my satellite, or the mass of my rocket here, the mass of my rocket here. They cancel one another out, so the m's disappear. So then I get that the escape velocity squared is 2gm over re. So the escape velocity is the square root of 2gm over re. That's where we get the escape velocity equation from. And I went through all this. I apologize if you struggled a little bit with the algebra. It's worth thinking about it a little bit more, maybe rewatching this part of the lecture to try and go over it again. Literally write these equations as I'm doing them so you can follow what's going on. But here's the reason that I want to talk about this. If you escape with exactly the escape velocity, that is, if I threw this ball at exactly the escape velocity, it's going to get slower and slower and slower, and it's going to continue to slow down until it reaches a speed of exactly 0 when it's infinitely far away. But now imagine that I run that backwards. Imagine that I take this object very far away and it's not moving at all, and I let it fall towards the Earth. Well, in physics, we can take the reciprocal of something in a simple system like this, and the reverse is the same. We can run time. You think of it as running time backwards. So instead of the ball escaping out to infinity, I can now let it fall towards the Earth. It's going to accelerate towards the Earth just like it was decelerating as it went away. And what that means is if I take a ball and put it very far away from the Earth, and I let it fall to the Earth, it's going to start with 0 speed very far away. Well, by the time it reaches the surface of the Earth, it will have the escape velocity. And what that means is when a satellite is approaching a planet As the satellite gets pulled into the planet's gravity is pulling on that satellite. It's accelerating that satellite so that by the time it reaches the surface of the planet or close to the surface of the planet, the satellite is traveling with the escape velocity. If an object falls to Earth from very far away, when it hits the surface of the Earth, it'll be traveling at the escape velocity. As we send spacecraft to Mars, and as they approach Mars, the gravity of Mars is pulling them in. And that gravity is pulling them in so strongly that by the time they get close to the planet, they're traveling with greater than the escape velocity because they didn't start at zero. They started with some speed that we had sent them from Earth. They're traveling so fast that if they don't slow themselves down, they'll just fly right past Mars and escape out the other side. To get into orbit around an object, we have to slow ourselves down. We have to fire our engine to slow down because the gravity of the object gives us the escape velocity that's required to escape out the other side. Let me do a quick case study here, just if you're curious. What was the very first spacecraft ever to escape from the human man-made spacecraft ever to escape from the surface of the Earth? Well, that was the Soviet Union's Luna 1 spacecraft. And interestingly, it was unintentionally the first spacecraft to escape from Earth. So a little bit about Luna 1. It was a probe launched on January the 2nd, 1959 from the Turyatam, which we now call Baikonur Cosmodrome. It was an 8K-772 rocket. It was derived from the R-7 ballistic missile. The early Soviet rocket launches, Sputnik and in particular, in this case, Luna 1, they were launched on this rocket, which was actually just an early version of an intercontinental ballistic missile, an R-7 ballistic missile. Now, they tried launching this lunar probe a couple times. The first 3 ended up with rocket failures. The Soviets ended up sending about 40 missions to the moon. The last one that they sent to the moon was in 1976. That was Luna 24. About half of the satellites that they sent to the moon were successful. Luna 24 was one of the rovers that they sent to actually drive across the surface of the moon. And then they had other samples, missions that picked up samples and returned those to the Earth. But let's go back to Luna 1 here. So in Luna 1, the spacecraft was 361 kilograms. And it was intended to impact the surface of the moon. So it did not have thrusters on board that could slow it down to get into orbit around the moon. So when it got to the moon, it would be traveling too fast to go into orbit. So the intention here was to literally shoot it and aim it towards the moon and have it hit the surface of the moon. But here's the problem, right? The moon is moving. So in order to hit the moon, you have to plan to aim it not for where the moon is right now, but where the moon will be when this thing is going to get out to the distance to the moon. So that requires a fair bit of calculating, but they did all those calculations. They figured out when they needed to launch it, what speed they needed to give it so that it would get out there and it would hit the moon. It was carrying a couple pennants, a couple flags with it. It had the pennants had on them the Soviet coat of arms. There was a suite of scientific instruments on board. There was a transmitter. There was a system to send data back to the Earth right up until it crashed on the surface. There were batteries. There were the scientific instruments included a cosmic ray counter to count high energy particles coming from our galaxy and from our sun. There were gas and particle counters to count the density of gas in the space between the Earth and the moon. There was a solar radiation experiment on board to measure the total amount of energy coming from the sun. There was a magnetometer on board to measure the Earth's magnetic field and the moon's magnetic field. And then the third stage of the rocket even had some sodium inside that it would release into space. And as sunlight hit that sodium, it would excite the sodium to glow. And they were going to do an experiment to use that to look at magnetic fields and other things. So lots of experiments on board. However, there was a slight problem. The way the rocket was launched was they needed the stages to burn for a certain period of time so that the rocket got a specific amount of acceleration and then shut down. But they didn't trust the timers that they had on board the spacecraft. So they actually used a radio signal from the ground to tell the rocket stages when to shut off. And it turns out there was an error in the ground equipment. And the error in the ground equipment let one of the second stage burn a little bit too long. And because that upper stage burned a little bit too long, the spacecraft was traveling a little bit too fast. Because it was traveling a little bit too fast, as it went out to the moon, it didn't hit the moon, it passed in front of the moon. But this also meant that it had enough speed to escape from the Earth. And so Luna 1 was the very first human-made object to escape the gravity of the Earth. It flew by the moon about 34 hours after launch. It was about 5,000 to 8,000 kilometers in front of the moon. And it was the first thing that humans ever launched that reached escape velocity. To this day, it is out there somewhere in orbit around the sun. You can tell from the size of this, it was not very big. It was about the size of Sputnik, roughly. So, it was a sphere about this big. So we're not worried about the fact that it's out there in orbit around the sun. It's minuscule, tiny, but it is still out there somewhere in orbit around the sun. In the end, the probe didn't detach from the third stage as was planned, and they eventually lost contact with the spacecraft about 62 hours after launch, when it was not quite twice the distance to the moon. So at the time, they hadn't given it a name, but in 1963, they recalled this mission Luna 1. So that is the first vehicle to escape from the Earth, to reach escape velocity. So this concludes Lecture 3 on gravity. In our next lecture, Lecture 4, we're going to take a look at orbits. And we're going to study lots of details of orbits. We'll study Kepler's laws of orbital motion. We will study the different types of orbits, and we will study the characteristics of an orbit. Today, we talked about perfectly circular orbits, but there is no such thing in the universe. All orbits are slightly elliptical, as we will find out, and you can make that ellipticity work to your advantage. And so we will talk about reasons for making orbits elliptical and how we can use that to modify the orbit of the spacecraft. So join me in Lecture 4 when we talk about orbits.